Now we will start with RNN model as well as LSTM model in a single data set. What is RNN? RNN basically stands for Recurrent Neural Network, and what exactly it does? It is similar to our traditional artificial neural network, but it generates two output. First output is gone to the next layer, and second output that it is getting generated, it is passing out on to the next timestamp. So if you talk about this feed forward neural network, this is our simple feed forward neural network. These are our inputs, and we are for this inputs a certain y output is getting generated. Okay, but here in this feed recurrent neural network, it is generating, it is taking inputs, it is processing the inputs, it is generating an output, but it is passing this passing a part of this output or hidden state to the new or the next neuron or next row. Okay, so basically what it is trying to do, so the objective of RNN is to preserve the previous memory and utilize the previous memory so as to give output for the current. So whenever we see an association of data where the previous information is relevant to the current output, so there we can use RNN. So RNN takes the output of the previous neuron, okay, output of the previous processing, and that output is also utilized for the current processing. So this particular information basically passes on to the next neuron, which is same neuron for the next iteration of data. So if you want to understand it better, so we can see here how this neuron works. So X is a neuron. This is a simple RNN architecture which we have where it will be some input data will come, and this input data will have certain weights, and it will be processed in this neuron, and some output will be getting generated. Okay, so this output is getting generated, but there is a hidden state which is getting generated back in this data. So if you see how this works, so this is our neural network or neuron, a single RNN neuron, and this RNN neuron is at timestamp t-1. This timestamp t-1, the input at timestamp t-1 is taken, it is processed, and output is getting generated L, and it is also generating a new hidden state V. This hidden state V is getting passed on to the new set of information. When I talk about new set of information, it is not the new layer, it is the next data set or next row in the data set, and in this next state or row of the data set, it is taking information of the current row of information as well as the previous information, part of the previous information, and it is going to generate an output LT. Also it will generate a new information it will also pass this information to the next state after or next row, which means the processing of a single information is not only dependent on the current row, it is also dependent on the previous row. So this is how a traditional RNN works, and this is useful because whatever decision making we are doing in deep learning, it is dependent also on the previous observation of attributes. So that is why it is important. So now let us talk about RNN in detail and the implementation of the RNN. So first of all, we will import NumPy. We know what is NumPy. It is used to process numerical array and numerical operation. We will call TensorFlow. We will be using a textual data now because RNN and LSTMs are usually used on a textual data. So we are going to use a text processor, which is tokenizer, and after that we are going to use sequence. We are going to use paired sequences. We are using sequential architecture to build up multiple layers. Now here we are using embedding layer, simple RNN, and dense. What is this embedding? Embedding is used to convert textual information into a meaningful information. So it kind of helps us to restore semantic or meaningful information from a text data. Now we will read the data. So we are using this Twitter comments class.csv. This Twitter comments class.csv is a set of tweets tweeted by different gamers on different games, and they have generated different tweets out there. So if we talk about this data, so this data has serial number, tag, sentiment and tweet. Earlier it was not there. We have set the new column names, that is serial number, tag, sentiment and tweet. Serial number is this, which means this is basically uniquely identifies a player. So there is a player with 2401 as a serial number, and he's playing Borderlands, and his sentiments are assumed to be positive. Someone has tagged his sentiment as positive about the game because of the content, that whatever tweet he has made, which means while he's playing that game, he's totally engaged into that game, and it shows that he is positive, like he likes that game, and that is why he has given such kind of comments. So the comments can be like anything. Now gaming comments are different from the natural language comment. Like normally what we are talking, if it is a product review or something, the comments will be different, but the gaming comments are different. So here we are trying to understand that whether he is positive about this game or not. Like this comment will decide, this tweet will decide whether he is positive about that game or not. So we are all talking about this positive. If you want to see all the data set, we can definitely see this data set. Okay, kind of the algorithm is processing, so maybe that is the reason. So let us move forward. Now we will talk about the data set, and we will see if there are any missing values. So there are 848 tweets which are missing. So when we talk about missing value treatment, it is not possible to treat missing values directly in this data set because it is a comments, or it is a tweets given by one. We cannot put something which is fabricated, like we have done in any other machine learning algorithm or any other algorithm where we can use mean, median, mode imputation, where we can use forward or backward fill. Here we cannot do it, okay? Or for example, we are using KNN imputer. We cannot use any kind of imputer, so we have to simply drop these rows. We can use it KNN imputer, but right now it is free, and it is fair to drop the rows wherever missing values are present. So we have dropped the missing values. We are dropping the we are seeing the shape of the data. Now we are left out with 73824 73,824 rows and 4 columns. Now we will talk about sentiments. The sentiments are quite balanced. We can see negative sentiments are higher than positive sentiments. Now these are sentiments for all different games. We are not talking about a single game in general. So these are different sentiments for different games. We'll try to understand this sentiment. We'll convert this sentiment and store as val. Okay, val is a series now. Twitter.sentiment will store the sentiment as a series. Now we will use label encoder, and we will encode the sentiment column. So we will do the encoding for this val, and now we have labels as 33012 So there are 4 sentiments. So sentiments will start from 0 to 3. So these are our sentiments, and now we will also store the tweets. So we will store the tweets as sentences. Okay, so we are storing the tweets as sentences, and we will talk about the first sentence or the first tweet. It is, I am getting Borderlands and I will murder you all. Basically this shows that this guy is totally involved and engaged in this game, and it shows that yeah, he's positive, like he's happy with the game. So that's what we are seeing here, and then we talk about the different processing. So first we will process the data. We use regular expression to clean the data. So here what we are going to do is we are going to use a sort of natural language processing. A simple processing we will be doing. We will use NLTK library. We will use stop words, Porter stemmer, word net limitizer, and we will use TF-IDF vectorizer, train test bed, and we are using stop words, wordnet, and ordinary multilingual word 1.4 version, dictionary or corpus of word. So these are different things that we are going to use today, and we will explain this at the time of implementation wherever we are using. Now starting with stop words first. So we are creating a set of stop words. Now what are the stop words? Stop words, basically when we talk about natural language processing, and what we are doing in natural language processing is we are trying to convert a human natural language into machine readable language. So the comments that we have seen so far are not at all, like the machine will not be able to understand what this comment is all about. For him it is just a text. Okay, so he will not be, the machine will not be able to understand what this text is. So we have to make him understand. So in order to do that process, we have to do certain steps by which we can create that sentence into a machine readable or for a machine readable machine value or a equally equivalent machine readable information. And for that we start with certain steps. So when we talk about normally when we are talking in a natural language processing, so the words which are very frequently used have very less weightage in a discussion. Okay, so when we are talking about such words, so such words are is, are, at, the, that, why, that's why, all these words are more commonly used in a discussion, and that is why these are not relevant for machine. For a machine it is just an word which is an extra, so we need to remove all those words. So that is why stop words are these words which are used very commonly in a discussion, so we will call it as stop words. And we will kind of create a set of stop words and use it for removing it. Then we will use Porter, stemmer and lemmatization. Now see, whenever a word is there, that word will have multiple version. For example, played, playing, player, players, all these different set of words are originating from the word play. So we are not supposed to use all these words when we are developing. So when we are cleaning a text, what we are going to do is we are going to represent each word as a column. Okay, that is what going to be our numerical information or information which is going to be fed to our RNN LSTM network. So when we talk about this data which is textual in context, so we are going to convert, we are going to have a sentence, we will remove stop words from the sentence, and whatever is left out we will trim that information. Okay, we will use that information, and whatever words are there we will convert that words into columns. Okay, so if we have multiple type of words like player, play, plays, playing, all these different words are originating from a single word which is play. So which means play is important. The alternatives or the derivative of the word play are not important here, because they basically represent the same act, that is play. So in such instances we have to trim out all the additional information. To trim out this additional ing, ed, er, prefix and suffixes, we use stemmer. Stemmer will remove the prefix and suffixes from the word so as to have very less number of words, because see, when we have lot of sentences we will have lot of words, different words, and for this lot of words we will have multiple columns, and we have to reduce the number of columns. Why? Because RNN LSTM network, whatever network we are talking about, require less information or less number of columns. If the number of columns are more, it will increase the problem of dimensionality, and that will reduce the efficiency of the model. So that is why we apply stemming, which means player, playings will not be 3 different columns, it will be just a single column called as play. That we do with stemmer. And then we have lemmatization. So lemmatization is all about bringing the word to its root form. For example, if I have 3 different forms of word, good, better, best, something like that, like I'm not giving you the literal example, but these 3 are positive, superlative and positive, comparative and superlative degree of a word. So the base root word is good only. Okay, so lemmatization is all about converting any word into its base root form, which means even if there are occurrences of good and best in a particular sentence, it will only use good, best will be totally ignored. So the base root form of best is good, which shows if any kind of sentiment across that word. So basically if 2 words have different meaning, same meaning, but both are kind of similar version of the same, so it will reduce it. So lemmatization is done based on semantic or meaningful information about it. So we are using WordNet lemmatizer, which is coming from the NLTK stem. So in the stemming part we have WordNet lemmatizer. Now here we are using ordinary multilingual word, that is 1.4, and according to it that is a corpus of set of words, and there we will have different set of lemmatization, stemmer, porter, and then we have we have stop words, whatever is defined in that corpus of words, we are going to implement that only. If you want to create your own set of all these algorithms, so that is going to be a totally different, and it will take a lot of time. So better we are using this ordinary multilingual word which is developed by NLTK. We are downloading it and we are working on it. So now we will start with cleaning process of the data. So for cleaning process, what we are going to do is we are going to take a text from we are going to take a text, and on this text we will convert it to string format and lower it. So once we lower it, we will anything, if it is capital, small, anything, it will get lowered down in the lower case, and then wherever we can see these two lines are responsible to convert or remove any special characters or any uncertainties or extra spaces from my text. So we are using regular expression here, and this is the regular expression that we are searching in that text. If that regular expression is there, so it will remove that regular expression with empty quotes. So it is happening for both here as well as here. So which means if there is anything which is completely against the regular expression, or which is completely against like if it has special characters or something like that, it will just remove that particular part. And once special characters and extra spaces is removed, then we will go on creating or doing removing the stop words. So now we will remove the stop words from our text. So for removing the stop words, we are using this list comprehension method. For example, if first I will do what, I will split the data text into different words, because I have already cleaned the data now. Now once I have cleaned the data, I will not have any extra special character or extra spaces, and we are using text dot split. So when we are using text dot split, it will convert the words into a list. So like all the words in that text will become list, and in that list I am iterating over each word, and while iterating over each word, if that word is present inside the stop word, I will not use it. I will not add this word in this list. Okay, so what I am doing is, if the word is present inside the stop words, I am not adding it. If it is not present, then I am going to add. So that is why I am using if word is not inside the stop words, whatever word in that particular list, okay, is not inside this stop words, I am going to add it in this list comprehension list. Okay, so after doing this operation, I am removing all the stop words which are there, and after that I am using dot join function. So now we are talking about cleaning the data. So we have the text, we have information in the form of text information, and we have treated the text information. We need to treat the text information, like for example, we have a text written by someone as a comment or tweet. So we need to remove unnecessary information, because if we do not remove it, it will just get overloaded, like the model will get overloaded with junk information. So first thing what we will do, we will create a function called as text cleaner, and text cleaner takes textual information as an input, and first thing we will convert this textual information into string. Why we are doing it? Because maybe in certain regions we have numeric information as well, so we will convert that as well into text. We'll convert it to lowercase after converting it to text. And then why we are converting it to lowercase? Because capital word and small word will be considered different if we do not do it. So that is why we will convert everything into smaller case. And in these two lines we are removing a special character and extra spaces. So we are using regular expression to detect if a particular regular expression, for example empty space, is not present. So wherever is the empty space, it will remove it with empty blank quotes, and wherever it is present or any special character is present, it will remove it with blank quotes, like it will replace it with blank string in the text that we have provided. After that, we will use list comprehension method to check if a particular word is stop word or not. So after cleaning the text, we will not have any special characters, empty spaces. So now we have only words inside that text. So we will use the split method. Split method is going to convert the text into list of words. So once we convert it into list of words, we will see that if that word whatever we have converted is present inside the stop words. If it is not present in the stop words, we will put it into this list, otherwise we will not. The meaning is, if that word is not a stop word, we will place it inside this list. And we are using join method. Join method, we are putting some space over here, space, because in this list it is going to be a list of words. We do not want list of words, we want a text in entire comment. So we have removed the stop words, and we have we are joining that words after removing the stop words. So we have removed the stop words, and we have a text which is free of stop words, and this text is again used, and on that text we are going to apply the stemming operation. So here we are not removing anything, we are just applying stemming. What is stemming? Stemming is a process of converting that word into the base root form. Okay, so when we talk about the base root form, which means we are going to remove the prefix and suffix from it. We can also do lemmatization here, like here we can remove this and we can do the lemmatization. I have already given the code. So lemmatization will do what? It will create a word of base root form based on meaning, okay, based on literal English meaning. Then we will return that text. Basically what is happening here, we are taking a text, we are cleaning it, doing stop word removal, doing stemming and lemmatization, and giving a text which is free of stop words, which is free of lemmatized version of words, and which is also free from any special character. So we have a cleaner text here. Now we will create a column called as comments clean, and this comments clean column is it will have all the text which is refined with respect to this text cleaner. So on the original tweet column we are going to apply text cleaner function. So we are using the apply method. So Twitter tweet dot apply, on this we are going to apply this function text cleaner, and automatically we are getting a clean version of text. As you can see, earlier it was written im getting on borderlands, but now we can see getting is becoming get, on is getting removed because it is a stop word, borderlands is becoming borderland, murder is there, and rest of the words will be there. Similarly all other words like just realize that the Windows partition of my, and you can see just is getting removed because it is considered as stop word. Realized is become realize, okay, ed has getting removed because it is just using the stemming operation. So now earlier we had suppose 10 words, now we have only very few words. Here also we have more words, but here we have very less words. So we have kind of cleaned the data, and this is our first sentence. Now we will do the act of tokenization. But now whatever we have converted or cleaned, we need to use it for model building. So we will first create it in a machine readable format by using tokenization. Now what is tokenization? Every word will become a token now. So for tokenization we are using tokenizer, which is present in NLTK, and we will clean all the sentences and we create the clean sentences. Now tokenizer dot fit on text. So we are going to apply tokenizer method on clean sentences that we have just developed, and we will use word index. So word index, if you want to see, so tokenizer dot word index. Now what is tokenizer going to do? Tokenizer is going to assign an index to each and every word which is cleaned version. So game becomes 1, play becomes 2, getting was converted into get, and get becomes 3, like becomes 4, im becomes 5. Likewise these all words will get converted into some index. Some index will be assigned. Now these numbers represent a particular word. Every number represents a particular word. This we have to keep in mind. And then we will apply tokenizer to tokenizer, and we will convert text to sequences. So we are going to create sequences of this tokens. Okay, so if you want to see sequences, we will talk about sequences. So sequences are basically this. So this is 5, 3, 69, 1164. So what is this 5, 3, 69? You can refer here. 5 is basically im, 3 basically is get, like that. So these sequences are the encoded version of your word, which is getting developed by WordNet tokenizer or tokenizer. Then we are going to use max length. Why we are using max length now? We need to identify the longest sentence which is there inside my data. Why we are doing it? Because we also want to do paired sequences, because whenever we are creating an array, the array should be uniform. It should not be that the first row has only 3 words, like here we have only 4 words, here we have only 3 words. So it is not uniform, the data is not uniform. When we want to feed this to a neural network architecture, the data has to be uniform with respect to rows and columns. Certain rows have only 3 columns, certain rows have 5 columns, certain rows have 10 columns. So what we will do? We will do padding operation. The padding operation is all about adding extra rows. Wherever we have extra rows, we will put it as 0. So for that we will use paired sequences. Paired sequences will take sentences which we have developed, or the sequences we have developed, and it will pad with respect to maximum length. It will use 0 padding, which means wherever the words are not present, it will put it as 0. So it will create an array of 163 dimension. Why 163? Because the maximum length of a particular sentence, maximum length of a particular sentence, which means a sentence having maximum number of word is 163, and there are 73824 rows into it, and we will use so this is our sequences. If you want to see paired sequences, you can see this is the padded sequences. Okay, so if we talk about sequences, so sequences 53691164, this is our sequence. The padded sequence version is 000, and here we have 5369691164. So what are these 000? These 000 are basically other words. For example, in our statement, it was im get borderland and something like that. The word was there. Okay, im getting borderland and something like that. The word was there, but this is in the sentence number 1, only these words are there. That's why we are getting indexes for these words. In some other sentence we have some other words. Okay, say play cricket, something like that, play cricket. So play cricket, maybe play cricket index is something else. Say play is here and cricket is say somewhere here. So these are two different words, right? So in the sentence where we have play cricket, so the paired sequence will be different. So here we will have 0 in all places except this place where we will have the value of the token, or the index value of the token. So this is how we are arranging the data in a form of numeric representation, and then we are using clean sentences. We will see that clean sentences is im getting borderland murder and im getting borderland murder. This is how it is represented, and sequences is quite different. Okay, now we will use labels.shape to see what is the shape of the data. np.unique labels, so to see how many unique labels we have 0, 1, 2, 3, which means 4 unique labels we have. Now we will use RNN model. So in RNN we are using embedding dimension of 16. Embedding is the process of converting a corpus of word or a token of word into a meaningful architecture of words. So we are using vocab size of length of word index plus 1, which means the size of words that we are using. What is the total size of the word? So we have word index, total word index, how many total words are there in all the possible words, and we will use model, we will create sequential model. So sequential model, first layer that we are talking about is an input layer. So input layer has to be embedding layer, because embedding layer will convert that input information into a meaningful information, and we are going to use vocab size as the input size, and embedding dimension is 16, that we can fine tune, and it basically represents how we want to do the embedding of the data. Input length we are going to use is the max length. So max length is the total length of number of columns. So the input length is going to be total number of columns. Then we are applying the simple RNN. So we are applying simple RNN with 32 neurons, and we are using dense activation function, which is having 4 as the output, because this is an output layer. So output layer we have 4 neurons, and activation is softmax. So this model takes input, it converts it in the embedding layer, it converts it into meaningful information based on the word net we have developed, and it applies simple RNN over it and dense. So simple RNN basically takes information of the current row and also output of the previous row. So this is how it works. And then model.compile, we will compile with the help of optimizer, which is an Adam optimizer. We are using loss as sparse categorical cross entropy. Metrics, we can use accuracy. And model.fit, we are using padded sequences. Padded sequences is the numerical equivalent comment. So whatever comment we have created, the numerical equivalent of that comment is going to be padded sequence, and labels is the corresponding label to that particular padded sequence. And epochs, we are using 10, verbose is equal to 1. This is going to be heavy, so that is why we are keeping epochs as 10 only. And here what we are doing is we are just creating a sentence and testing this model. So we have created a sentence, this movie is amazing or something like that, and we convert the data, this comment, into a tokenized version of the comments. This is a simple word, so we are not doing any kind of cleaning process. We can do the cleaning process, it is very simple, we can do it, but we have just ignored it. We converted these words into padded sequences by using pad sequencing. We are using model predict. Model predict will model is our sequential architecture model. It will predict the padded test sequence that we have just developed, and whatever is the output, so it will give 4 probabilities as output. Out of that 4 probability, we have to identify which probability is maximum. So that we are going to do with the help of argmax, np.argmax, and that is nothing but the predicted output. Okay. So that sentiment of that particular comment, so sentiment of this comment, this movie is amazing, is what we are going to predict. Okay, whether it is positive, negative or neutral. Now we use this epoch by epoch. So in every epoch we can see there is a considerable improvement in the accuracy of the model. We have used very less number of epochs, so we are able to get very higher accuracy. And the sentiment prediction, it is giving 1 for that word, that is this movie is amazing. For this movie is amazing, the sentiment is 1. Now let us try to see what is the sentiment 1. So sentiment 1, so let me check what is the sentiment in the label. So if we talk about val, so val we can see positive, positive, positive. So positive is 3 in labels. So if you want to see what is the sentiment, let me le dot, we are going to use inverse transform, and in that we will pass on value as 1. Let's see. So 1 is negative sentiment. Okay, so it is telling us that the sentiment 1, so this comment that we have provided is a negative comment. So it depends on the model how it is trying to learn from the data. So maybe it is not able to correctly recognize the patterns, or maybe this comment with respect to gaming is maybe it is someone is saying in irony or something like that, so it is considered as a negative comment. So maybe such kind of learning our model is doing. So it is totally dependent on what information we are passing. So this is a comment which is negative, and this is how we can create a simple RNN. The objective here is to use a simple RNN model which can understand from the previous data. Now we will move on to the implementation of this model. So we can implement this model, or we can show it to someone who wants to just try to check out and play around it with the help of this Gradio interface. I will quickly go through it. We can simply get this code from the Gradio website. So what we are doing here is, we are taking Gradio as an input. Gradio is a website or a library which allows us to create a web interface. So for that we will take Gradio, we will import NumPy, we will import pad sequences, label encoder. We are going to create a predict sentiments as a function. So what is this predict sentiment function is going to do? It is going to take some text, it will process that text, and it will create a prediction. Okay, and it will tell after predicting whether it is in which class. Okay, it is, so basically what it is doing, it is using our model and it is predicting from it is taking a text and predicting whether it is positive, negative or neutral. So that is what this function is going to do. Why we are developing this function? Because Gradio interface requires a function. Okay, so we are taking Gradio interface here and the output is the predicted label. We are creating an interface iFace by using gr.interface, and in this we are passing in this function. This function takes input as a text and gives a prediction whether it is what kind of text it is, positive, negative, neutral. Inputs is equal to text we have taken. The input format we are taking is a text, and the output is also again going to be a text, but this is an input. So here we can type anything, but here we cannot because this is an output. We cannot type here in the output section. Title is sentiment analysis, and this is some kind of description that I am giving. Enter a text to predict whether it is positive, negative, somewhat like that. And iFace.launch, it will create this local host, local URL. You can also have a URL which is not local by simply putting share is equal to true, and that will create a URL which can be shared with anyone, which is only applicable for 72 hours. And in this I can simply type amazing or any word I am just typing with respect to the context of this game. It is telling that it is negative, and if I put something like this, kill you, so let's see what it is. It is telling that it is a neutral comment. I'll put unhappy and let's see what it is putting. So it is telling that it is a negative. So based on the information which is we are passing, it is going to just give us whether it is positive, negative or neutral. You can click on this link and it will open as a web page over here, the same exact. So this can be used for someone who wants to share it with like create a shareable version of your code. You can use it. Now now we have created this function. So this is just to text, we will ignore it. This is the same function that I have used here. So I'll just remove it and let us come over LSTM module. So now let us try to understand the next algorithm, which is the text processing algorithm, that is LSTM. So the problem with traditional RNN is it is able to recognize only the first few entries or the previous few entries, but it is not able to retain the long-term memory of that particular data. So when we are having such kind of scenario, then we can use LSTM architecture. So what is LSTM? So LSTM stands for long short-term memory architecture. So the problem with traditional RNN is RNN remembers only the previous memory, which means the very previous memory, not the old memories. So whenever it is a long-term memory, RNN is not able to recognize. So in order to overcome this problem, we have an architecture called as LSTM, which stands for long short-term memory architecture. So this long short-term memory network is all about retaining the very previous information as well as the current information, and recognizing whether the previous or the old memories are important or not, or whether we have to forget it or store it. So let's try to understand the architecture of LSTM in detail, and then we will try winding up with understanding LSTM in detail. So this is our LSTM architecture, and in this LSTM we will take memory as C of t minus 1. So let's try to understand. So this is our memory, which is then long-term memory we can call, long memory we can call, and it is also called as cell state. In LSTM we have different gates. This is our hidden gate, input gate, this is our forget gate, this is our input gate, and this is our output gate. So these are different gates. We can see clearly it is mentioned what are these gates. And in forget gate we have sigmoid activation function, in input gate we have sigmoid plus tanh activation function, and in output gate we have only the sigmoid activation function, and this here we have tanh activation function, which is coming from the cell state. So these are different activation function which are there. Now let us understand what happens in this LSTM architecture. So LSTM has this old memory running. So old memory is a formation of different set of information from the older memory, and then we have hidden state. Hidden state is the very previous memory. So hidden state will have memory from the previous time stamped, okay, which means say if I am talking about an episode, okay, if you are watching a web series, so HT-1 is the previous episode, and CT-1 is nothing but all the collective memories of previous episode as well as today's episode or yesterday's episode, not the today's episode. So it is a collective memory of all past episode, and this is the memory or information of the current previous episode, okay. So this is the difference between this long memory and this hidden state, okay. Now we will talk about input X. So this is the today's episode. We are trying to remember today's episode. We are entering this information of today's episode as well as yesterday's episode. So we are taking today's episode and yesterday's episode, and we are passing it into this forget gate. So forget gate has sigmoid activation function. Sigmoid activation function helps to store the information whether it is relevant or not. So it will convert or process this information on a scale of sigmoid activation function with respect to probability values. It will generate a probability value, and it will tell us that whether it is this information which is coming from the current input information and hidden information, whether this information is relevant or how much it is relevant to the old memory, how much it is informative to the old memory. Okay, so based on this sigmoid activation function, the probability value is generated, and that probability value is nothing but our current memory, and this current memory will go into this old memory. When it is going to this old memory, we can see there is a dot product which is happening, where we can see there is a dot product. So if this probability value is very low, say if it is 0, which means this current information, when we process it, we have the value 0, and when this 0 is getting multiplied with the old memory, it will nullify all the information which was coming from the past. Or this current input information is responsible to tell us that whether we are going to keep this old memory or at what proportions we are going to keep this old memory, whether it is relevant or whether it is not. That is why this forget gate, we call it as a forget gate. Say if the output of sigmoid activation function is 0, so if it is 0, then when we multiply it with old memory, it is going to forget the old memory, and the output, the multiplication of 0 with this old memory, we are getting output as 0. So that is why it will forget the old memory, and that is why it is called as forget gate. Forget gate responsibility is to just take today's information and yesterday's information and see whether it is relevant or not with respect to old memory, and if it is the old memory is not, if it is not the information or the product, whatever is the output value, if it is very low, it will reduce the old memory value. And this is how the old memory value, whether it is going to get expanded or reduced, will be decided with the help of forget gate. If the value of sigmoid activation function is very high, it is closer to 1 or greater than 1, if it is closer to 1, which means that the today's episode was very interesting, and we are going to add this episode with the we are going to multiply that value with the old memory, and it will increase the old memory to some extent or keep it as it is. Okay, it will keep the old memory as it is, or it will reduce the old memory. That is what this forget gate is going to do. The objective of a forget gate is to either forget something or either keep it as it is. That's it. So that is our forget gate. Then we talk about input gate. So in input gate we have two parts, that is first is input T and this is CT, candidate memory. Input gate has input memory. So first what we will do, we will pass in the hidden state and input state into this input gate, into this sigmoid activation function, and we will pass the same to the tanh activation function. When we are passing it to the this sigmoid activation function, similarly the same way it will decide whether it is relevant to the current information or not. If this value goes very low, the product of this input information or the memory that we are having today and the process version of today's information, the product is also going to be low. So tanh is going to do what? Tanh is going to convert this information into minus and plus 1. Minus means negative memory, plus means positive memory. So when it is converting the number into, say, whatever value, minus 1 or plus 1, this IT, this information will reduce the effect of, if this value is very low from the sigmoid activation function, it will reduce the effect of this tanh because we are having a product of it. Otherwise it will keep it as it is. If this value is 1, it will keep the tanh value or today's information as it is, whether it is positive or negative memory. Say if it is positive memory, it will go here and it will add to the long term memory. It will get added. So long term memory, if the forget gate has spared it, forget gate has told that no, this current information is relevant, and let us keep the memory as it is. So it will, a new value of the current episode will also get added to this existing pool of information. And once that is done, this combined memory will go inside this. So we have added memory of the today's episode. We have added memory of the today's episode. That is why it is called input gate. This is adding input to our today's episode. So now we will take the cell state. Cell state is a combination. Now in the output gate, we are going to take the cell state, which is nothing but today's memory and yesterday's memory. And we are passing it our input information as well as hidden state here in this sigmoid activation function. So this sigmoid activation function takes the today's information and yesterday's information. It will take the long term information of today and yesterday, and here it will apply sigmoid activation function. So sigmoid decides whether it is relevant or not relevant. If it is relevant, it will multiply and keep the yesterday's information as it is, which means, so we have this long term memory coming in. This long term memory is put in the 10H activation function. It will convert the value into -1 and +1. So if this long term memory is good, it will go in the positive direction. If it is not good, it will go in the negative direction. So you say if it is positive, so we have added today's memory with filtering it with respect to softmax function, sigmoid activation function. This sigmoid activation function. So now the 10H activation function takes the old memory and old and the current memory basically. Now here we have added the today's memory, right? So it will take today's and old memory, and it will scale it on a scale of -1 to +1. Okay. Now we will decide that whether like this hidden state and today's memory, like yesterday's memory and today's memory, will go inside this sigmoid activation function. And this sigmoid activation function, whatever is the output, it will be multiplied with this 10H value. So whatever is the output of this 10H, will multiply it. And the purpose of doing it is just to see that today's memory or today's information is relevant and contextual with respect to the old memory. So old memory is added, today's information is considered whether it is important or not, it is also added, and the old memory in combination with today's memory will come here, and the relevance of old memory and today's memory is decided here. It will go inside, it will get multiplied. If the value of sigmoid is 1, definitely as it is today's memory and old memory will be passed on to the hidden state. If it is not, so reduced version of it will be passed on to the hidden state as well as the output. So this is the output gate, and this is going to give the output of this neuron, and this is the hidden state HT, and this is the cell state CT. So cell state CT is a formation of previous memory, and whether it is whether we are forgetting anything from the previous memory or not, and today's memory will be added it or not with respect to the processing done here, and whether if it is added as it is, the cell state will move on forward. So what is the cell state? Is a combination of old memory and today's memory if the forget gate has spared that particular memory. So this is our hidden state HT, and later on it will move forward and it will keep on like we will have similar architecture of LSTM ahead, and it will take like that. So this is the timestamp HT -1 and this is the timestamp HT, and it will, the information is going to go to the next timestamp. So that is the difference between RNN and LSTM. So LSTM takes into consideration the old memory, while RNN doesn't take into consideration the old memory. So now we will build up the LSTM model here. So LSTM model here we are going to call with the help of layers. We are going to call the LSTM layer and dropout layer, and we are going to create a model complex LSTM, which is a complex LSTM model, and we are going to use sequential architecture over here. And on this sequential architecture, we are first taking input as embedding layer. Embedding layer, why we are taking? Because embedding will enable the meaningful information of the word net that we have created, or the word indexes that we have created. So vocab size is decided according to the so we are going to use the same vocab size because the data set is same. embedding dimension is going to be the same that we have used previously, and input length is the max length. So here it will tell us that how much input we are taking. So what is the token size? So we have 163 as the token size, or the total number of columns. We are taking that many number of columns. We are using LSTM now. So LSTM, we are using 64 neurons in this LSTM, which means we have 64 such kind of neurons, similar neurons parallelly, and these are similar to it. It is connected to the to current layer as well as the upcoming data points. Then we are using return sequences as true, and return sequences to get the output of the current layer as well as hidden state. We are going to create it. Then we are using dropout layer of 0.5. So we are going to drop out the LSTM networks. Here we have 64. Here we have 32. So like we are partially connecting these two LSTM layers. Then we are using dropout of 0.5, and we are connecting it with the dense layer, activation layer, with 64 neurons. So which means this layer and this layer will get connected partially with 64 neurons. And then we are using a dense activation layer with 4 as an output, because this is an output neuron or output layer. And then we have the softmax as an output, because classification has to be done always in the form of softmax. Now here we will implement or compile this LSTM architecture. So for compiling this LSTM architecture, we are using this Adam optimizer. We are using loss as sparse categorical cross entropy, and metrics we are using as accuracy. Then we will fit the data on this LSTM that we have created. So we are using padded sequence, which is our input data. We are using labels, which is our output data. Epochs, we are putting 10, verbose equal to 1. So this will take a lot of time because we have multiple layers here, and it is embedding also is going to happen. So it will take a lot of time. After that, once we have done, we can see there is a considerable improvement in the accuracy level of the model, and it is also taking into consideration the old comments as well. So which is actually not to be there in this scenario. RNN is fine. We can use RNN there, but yeah, which if we are using context also, the old context, so that will definitely help us whether to recognize a comment as positive, negative, or neutral. So we are using the same comment over here, and but the only difference is the model that we are going to use is LSTM model. And once we use this LSTM model, we'll see that what kind of category this particular comment stands into. So it is in the 3 category. 3 basically represents positive. So this is a positive category. Now we will see the Gradio interface. So we are using the same Gradio interface to create a web interface of the comment, and we are using the same process entirely. We create a function. The only difference is this function has model complex LSTM as the model of prediction. It is not RNN model, this is LSTM model, and it is going to give us a predicted label on that data, which means it will take some text and it will tell us that what is the category of that text. And we are using gr.iface and gr.did interface, and interface we are going to use there are two, we are taking function, and we are taking text as input, we are taking putting text as output. This is the title and description, and when we launch it, this is the web version of it, and this is where we can put any text. We can put just amazing or something, and let's see what is the output, and it is showing that it is positive, which means LSTM model basically works better than this RNN model because it takes into consideration the previous memory as well. So this is how a LSTM architecture or model basically works. So that is this is how basically RNN and LSTM can be used for working on text classification data. So we have seen text classification, how we can do it with the help of deep learning model. We have seen image classification, how we can do it with the help of deep learning CNN model. We have also seen what is regression, how we can do it on using the ANN model. We have also seen classification, how to do it using ANN model. We can implement any kind of classification regression task that we want to do using this ANN model or deep learning concept. So it is similar to machine learning, but yeah, we can do a lot of detailed neural level analysis of any data using deep learning.